In this video, we are looking at the Memory Profiler version 1.1 package. It takes a snapshot of the memory usage at a specific point in the game and gives detailed statistical breakdown of how the memory is being used. It can be run alongside the Unity Profiler and Profile Analyzer to implement optimization techniques to ensure the game runs smoothly on all devices. You can compare before and after snapshots to see what effect the optimization techniques have had on performance. To find out more about profiling and implementing optimization techniques, download the ebook from the link below in the video description. If you want to follow along with this video, you can create a new project in the Unity Hub and download the URP 3D Samples Scene template. It features environments to help you learn how to use URP optimally across all platforms. It has 4 environments, each with different art styles, rendering paths and scene complexity to represent the variety of 3D projects built with URP. Memory Profiler should be installed from the Package Manager in the Unity registry and find it in the list. For Unity 2023.1, Memory Profiler version 1.1 should be the recommended default, but if you're not seeing version 1.1 in the list for Unity 2022.2 and above, click on the documentation. Ensure it is set for Memory Profiler 1.1 and copy the package name here. In the Package Manager, click on the plus icon and choose Install by Name. Paste the name into the top field, and now it will install. It can now be opened from Window, Analysis, and Memory Profiler. I am using the Oasis scene from the URP 3D Sample Scenes. Once I start playing the game, I can then click Capture New Snapshot. It will display a warning on first use. This is a warning about sharing the memory capture files with anyone outside your development team, as it could contain sensitive data such as passwords. Read more about this in the documentation. Click the middle button so it will not warn you again. It will now take a snapshot. It then appears as a thumbnail in the snapshot list. We can stop playing and maximize the window. Click on the thumbnail to display the details. This diagram shows how memory is used in Unity. The section at the top is resident memory. This is the actual memory used in the system RAM. There needs to be enough actual space on RAM for the game to run. If the resident memory required is larger than the amount of actual RAM on your device, then it will cause your game to crash. Allocated is the amount of memory requested but not yet filled. This is what Unity expects could actually be used by this game. If there is not enough memory left in RAM for the allocated memory, it should not cause the game to crash, but it is something you should try and avoid by monitoring your game's memory usage. The physical footprint is the memory used by Unity to run your game, and is the resident memory plus the process compressed pages that have been passed to compressed memory storage. To understand this in more detail, click on the link to the Unity blog in the video description below. In this snapshot, we are using 2.68 GB of my total 32 GB of RAM on my device. Now remember that other apps and systems may be running external to Unity that also use some of the overall amount of system RAM, so memory should be kept below 70% of physical memory. We can see here the 2.68 GB of resident memory used and the 4.11 GB of allocated memory, although that is not yet filled. The summary page gives a quick overview of how memory is used in your game. There is a warning about taking snapshots directly in the editor. The memory usage is combining the Unity editor memory with the game memory, giving an inflated value. So for more accurate results, build the game, which we will cover shortly. The 4.11 GB of allocated memory is distributed across these categories here. Click on any of these categories for a description in the panel on the right. All memory sizes for graphics are estimated, Managed memory gives you a breakdown of the memory directly related to C# code in your project, the packages it uses and the parts of Unity's core that are written in C#, as opposed to the native memory used for C and C++ code. It consists of managed objects, empty managed heap space, and the memory that is necessary to run this code in the virtual machine of Unity's scripting runtimes, Mono or IL2 CPP. These virtual machine environments provide easy access to and controlled management of all C# object memory because the managed garbage collector monitors which objects are still referenced and which ones can be collected, and thereby have their space freed up for new allocations. The system also expands the managed heap whenever you create objects that don't fit on the currently available free heap space. Then there is a quick overview of the top objects that are taking up the most space in memory. This is 1.43 gigabytes, which is only a portion of the total memory used. In the Unity Objects section, it lists all game-related objects currently using memory. Objects make up a proportion of the game's total allocated memory, in this case 1.43 gigabytes of the total allocated 4.11 gigabytes, as shown in the bar at the top. The objects are organized into categories and ordered based on the highest memory use. Many developers establish a memory budget before production to ensure as they are creating assets, textures and scripts that they will all fit into the target amount of memory for the intended device. This view is useful to check the overall category memory usage to ensure that they don't go over the memory budget. Data is presented based on allocated, native, managed and graphics size, which matches the allocated categories in the summary section. So we can see here how each object category contributes to those categories in the summary section. From Unity 2023 onwards, the objects breakdown will show the allocated space and the resident space. Now, working with resident memory amounts will lead to better optimization implementation. You can open these categories to inspect each item. Clicking on an item shows which objects are referenced in this item and a detailed breakdown of the native size and metadata for this item. A tip to reducing memory usage for items is to ensure that read-write is disabled if the item does not need to be modified during runtime. If we check Flatten Hierarchy here, it now displays all items outside of the categories and orders them based on size, making it quick and easy to find the largest items. Switch off Flatten Hierarchy to go back to a category view. You can also use the search bar at the top to find specific items you want to inspect. The All of Memory section is showing the total memory in Snapshot, which is 4.11 gigabytes. This is all memory that Unity knows about, which includes the game memory and also Unity memory and other systems necessary to run the game. In Unity 2022, this is just showing allocated memory, but in Unity 2023, it will also show resident memory. Native and managed both have a reserved subgroup, which contains reserved memory that Unity needs to run certain processes. Click on Reserved to read more about it in the panel on the right. There are also Unity subsystems which are required for Unity to run the game. To get an accurate breakdown of memory usage, you should build your game. Go to File, Build Settings. Now I have placed just the Oasis scene in the build. Development Build and Auto Connect Profiler should be checked on. In the player settings, I have the build set as windowed at 1920 by 1080 and running background unchecked. You could also test at different resolutions by typing different screen width and height here. Then you can build the game. Now it may take a long time for the first build. However, every other build iteration you do will be much quicker. After it has built the game, we can run it. Ensure the memory profiler is open. It connects automatically to the standalone build. Now I'm on Windows, so I need to press the Windows key to get my mouse back to return to Unity. Click Capture to take a snapshot. It may take a while longer for a standalone build. Ensure you click back in the game screen for it to complete the capture. This snapshot shows the difference between the standalone build and the editor play mode version. The standalone build is using 0.52 GB resident and 1.85 GB allocated. This is a big difference to the 2.68 GB resident of the editor play mode version and shows why it is preferable to run Memory Profiler against an external standalone build. You will also see big differences in the all of memory category as it is not running directly in the editor. I have exported a completely blank URP scene and captured a snapshot of that. This can be used to establish a baseline to check performance of the Oasis scene. Here we can see a blank scene uses 217.4 MB of resident memory and 0.83 GB allocated. You will see in the Unity object section that there are still a number of objects that are part of a blank scene and contribute to 230.9 MB of allocated memory. We can now use the compare snapshots to compare the blank scene against the standalone build of the Oasis scene. With the blank scene selected, we can click on compare snapshots. The blank scene is snapshot A. Click on the Oasis scene, which is snapshot B. It's now going to compare the two snapshots. This is useful as now we can see the specific contribution of assets in the Oasis scene to the resident and allocated memory. Resident for the Oasis scene is the difference of 310.5 MB. We can also see the differences of allocated memory by category, the managed heap and the top Unity objects categories. These can be useful when checking against memory budget targets. In the Unity Objects section, it displays orange bars to show differences between the snapshots. The All of Memory section also shows the differences in orange bars for Snapshot B or blue bars for Snapshot A. Once you have clear memory usage statistics, this allows you to state the minimum and recommended amount of RAM required to play your game. The snapshots you take will remain in the project until you choose to delete them. Right-click on it to either delete, rename, or go to the folder. From the folder you can make a copy of the memory capture file if you want to import into a different project or onto another computer. You can import memory capture files from other projects or computers by clicking this button. Compare snapshots can be used to compare against a before and after optimization to check that the optimization techniques you have used have had a positive impact. Here I am looking at before, which is snapshot A, and after optimization, which is snapshot B. The differences may very well be small. In the Unity Object section you may see very small bars, orange for snapshot B and blue for snapshot A. Clicking on an item will also show the differences between the two in the boxes here at the bottom. There is a difference of 24 bytes between 312 bytes on snapshot A and 336 bytes on snapshot B. And that brings us to the end of this video. We have looked at capturing memory management snapshots for games in the editor and also external standalone builds. We have gone through the data presented inside the snapshot to understand how memory is distributed through your game. We have looked at comparing snapshots as a baseline against a blank scene and as a before and after optimization. To discover more, download the Profiling for Unity ebook below. Thanks for watching.